Now we will see some training techniques and tips that we can use for training multilayer perceptron. At first, we know with neural networks that as we let the network to be trained on the training set, it can go into with really low error rate on that training set. So that model is prone to overfitting in the sense that it can reach really low error on the training set if we train it for a long enough time. And what we know with that is that it doesn't mean that the error will be lower on the set. On the contrary, in fact, we can see that after some point, the overfit will occur, and the performance, the generalization error will increase compared to some point before. For example, here we see this. We see that toward the high number of epochs, the training set is still reducing, but the validation set are increasing. So this is I would say not a good situation. We should not go that far away in the training. We should stop before. And in fact, we can see that the sweet spot here is around that place where we have the lowest validation test error. So this is the configuration, the moment in the training where the generalization is the best. And as such, we need to have some kind of validation set that is used to monitor the performance along the training, and that is used as a stop criterion. When we see that the error starts to increase significantly on the validation set, we should stop training, and we should use the network, in fact, that has the best performance on the validation set. So, for example, we can observe that here we reach a point where the difference, where we see that there was an increase of in terms of validation error that is significant. So we should stop there. And we will backtrack, in fact, to this point where we see that the validation error was the lowest. So this is the point where we will expect to achieve the best performance in terms of generalization. But this also means that we should split the training set that we have at end into really a training for optimizing the neural network and a validation that is used to monitor the generalization error. So we always need to keep aside a significant part of the training data to monitor this, to be sure that we are not in a overfit regime in our training. One other thing that we need to consider that is kind of different is what we call the generalized delta rule. That is an extension of the basic training rule that we defined so far with backpropagation, but has some extra components. So we can see here, this is the basic delta rule that we defined before. That is the rule to train a neural network with gradient descent using the delta. But we are adding here on the right side some more elements, and these elements are in fact the corrections, the delta that has been applied to the weights at the previous iteration. So we keep some memory, and we keep updating the weights according to the updates we made before. That is called the momentum. And the point is that this correction, this kind of memory element, is really good to smooth off the training. So we kind of make the update using the usual rule plus an alpha plus the momentum element that is parameterized by the alpha, and the alpha is giving us somehow the importance of the memory component, the importance of the previous updates that we keep inside our current update, and this parameter is called the momentum by itself. So it gives some kind of inertia to the gradient descent as it includes the correction from previous steps. So we kind of smooth off, because you can see that maybe corrections will kind of be contradictory, and the point of using a momentum will kind of smooth it us and get us to make updates in the direction that is coherent with the previous updates that we have made so far. Because what we need to figure out is that this correction that is coming from the last iteration is in fact itself including the corrections that has been done at n-2, which includes also the correction that has been at n-3 and so on. So we kind of keeping with like decreasing factors, still we are keeping information on the first updates, on the previous updates so far, And that is, I would say, that is making this kind of inertia that we have in by training with the momentum. This is some kind of illustrating this thing, without momentum, we have the blue line. We see that we are only using gradient here, and this is oscillating, you can see that the oscillation are still coming on, and we need several steps. And at every steps, we are kind of undoing what we have done at the previous step, because we are here always overshooting, the learning rate seems to be quite important. So we are overshooting at first, we are still overshooting at the second steps and third step and so on. So this overshoot allows us still to converge relatively fast, but we can do better. With momentum, we will somehow take into account the previous updates, and as such, the overshooting will be reduced accordingly. So it tends to smooth off, and we see that over time, it tends to really go toward the right side, because it is smoothing off the up and down corrections and keeping the right side corrections, which is current between the different steps. We can see this like, if we are skiing on a mountain and we are going in one direction downhill. So if we're going downhill in one direction, we are going faster and faster and faster. And if we go on small bumps and everything, we will just kind of smooth up the bumps. We will maybe jump in the air a little and still continue the same direction, which is not the same dynamic that going really slowly or just starting up, going down the hill, or maybe going into slalom. If we go into slalom, we will reduce the speed at which we are converging, and we will possibly kind of always going reverse according to the directions of where we were going at the previous steps. So this momentum element is good for that. It allows somehow to train with relatively high learning rate while smoothing off over the different steps, which is good for speeding up convergence, and which is also good to go over some local minimum, to avoid getting stuck in some local minima. With the momentum, we will just kind of smooth off, and we will go over that and reach possibly better optimum, possibly still local, but better than what we would have got before and where we will be stuck before. Also, the backprop, as we develop it here, is developed for a sigmoid transfer function. So this is one case. We in fact in practice with deep neural networks, we are using different transfer functions like softmax and ReLU for the hidden layers. But also for regression, we can use different models also. And we have linear functions, hyperbolic tangent functions, ReLU functions. These are all different transfer functions that can be used in our network. In fact, all continuous functions that are derivable in R can be used. And even ReLU is not derivable in R, but there is some act you can do that make it usable directly for training our models. So multilayer perceptrons are particularly suitable for regression. In fact, we can use a kind of model with one hidden layer with many sigmoid functions and one output layer that is a linear function. And this model can approximate most of the regression functions that we would like to get approximated. And from that, we will use the mean squared error as criterion to train our model. I would say then the multilayer perceptron is a good model for regression. In fact, it is working relatively well. Also, on another topic, we saw the derivation of backpropagation with a first order method with gradient descent, taking into account the first derivatives of our error criterion. But it is possible to do better than this with second order methods. And in fact, there are many second order methods that are known to speed up the convergence of multilayer perceptron. For example, we can use Newton's method, which is based on the expansion of the second order Taylor series. So like locally, we are expanding, we are making a local modeling of the function with the Taylor series, and using this as a way to approximate second order method and search for the plateau with that modeling. And this will correspond to that. So we will basically look for partial derivative equal to 0 with the gradient, first and second order gradient. And we get this kind of function. But we know that here the Asian, this component of that function is kind of expensive to compute because we need to inverse a matrix, and this matrix inversion can be pretty complex to do. And so, as such, we can make use of conjugate gradients, which will avoid this calculation of the inverse of the Asian matrix, while still giving us really good performance. So this is something that can be done. In fact, that is possible. It will speed up convergence. The bad thing with second order method is that it's not scaling well according to the size of our data sets. So possibly with really big data sets, we can just use first order derivative of gradient descent as we know this, or like stochastic gradient descent. It will do a really great job. And the amount of data that we have at end will compensate a lot in terms of converging to good solution compared to the fact of using second order methods, which allow us to converge in less epochs, but still maybe more expensive in terms of computation.